If I can
Okay, so let me introduce you. So our next speaker is Jeffrey Harris. He's a professor of economics at MIT and a medical doctor, I think. And so you will talk about the subway and the evidence that it facilitates the spread during early phase of New York epidemic, right?
Yes. How is my technology? Can you hear me good?
Yeah, very good.
The slides?
Okay. Yeah.
All I need to do is to figure out how to collapse the images so I can see everything. Okay. All right. Thank you for inviting me. I've attended several of the seminars. I've enjoyed all of them. Today, I will talk about evidence, and that's why this very long title starts with the word evidence. I will not introduce any mathematical models, although I will have something to say about the viability and the predictive value of compartmental models that all come from the original SEER model, and whether or not, especially talking about the very early stages of an epidemic, we need to switch to perhaps a network-related model, or perhaps a hybrid between a network and a compartmental model. I'm going to talk about the evidence that subways facilitated the spread of SARS-CoV-2 during the very early phase of the New York City epidemic. By the early phase, I mean the time period from mid-February of last year up until the end of March. And by the end of March, my talk will be over. With such a long title, the question is could I collapse it in any way? Let's see if I can, here we go. So here is the collapsed version. Evidence on the Big Bang in the Big Apple. The Big Bang, because we're going to talk, or I'm going to talk, about the very earliest evidence as to what happened, even before people knew that the virus was spreading quite widely within New York City, a region that has a population closing in on 9 million people. New York City is important because it turned out that by May, it was the epicenter of the entire epidemic throughout North America. The number of accumulated cases by May in New York City was larger than the total sum of all the cases of all the metropolitan regions outside New York within the United States. The number of accumulated cases exceeded the combined sum of cases in the autonomous community of Madrid, the province of Tehran, and Northern Italy combined. When I talk about evidence, I'm going to talk about several diverse lines of evidence. One line of evidence will be public health data. It will be numbers of cases or cumulative prevalence of cases. But I will also talk about genetic analysis of viral samples as being critical to our modeling, as well as data on entry into turnstiles, or basically entry into the subway system at various stops in New York City or throughout the city. And then finally, picking up on Olga's theme, I will be using mobility data extensively, but from a different source. So let me get started with the evidence. This is the number of counts of cases by borough in New York City, where New York City has 5 boroughs. Probably a better translation would be districts. These are not postal zones. These are actually fairly large conglomerates of neighborhoods, each with millions of people. Let's see if I don't see my mouse here. This is a problem. I'm going to go out of played mode and just go here. And although, can you see the mouse now?
Yeah, now we can see it. Yes.
All right, so this is not play mode, but it works anyway. Okay. Here is the first reported case from the Department of Public Health on February 29th. The cases are colored according to the 5 boroughs or districts of New York, which are color coded here. But you can see that by the 6th, that is within 1 week of the recording of cases, the cases are identified in all 5 boroughs throughout Manhattan, throughout New York City, including Manhattan, Bronx, Brooklyn, Queens, and Staten Island. Let me go to the next slide. Here are the same data collected in a different manner. In this way, these are the number of hospitalizations, and these data are retrospective data. So a person is hospitalized, and then later on, it may be determined that they had a SARS-CoV-2 coronavirus infection. And here we can see that even by the first day of March, all of the districts or boroughs of New York City are represented. Although these are the dates of hospitalization of these individuals, we have to work backwards. If we think of an incubation period of approximately 5 days, that is the date from infection until first symptoms, then we have to think further about the lag time between first symptoms and when a person is hospitalized, which is not well known, but could be another 5 days. People get sick initially, but it isn't usually until a good 5 days to a week until they're really short of breath and they feel terrible and it's time to go to the hospital. That would mean that the first infections likely occurred in New York City somewhere in the middle of February, well before anybody knew there were any infections. Not only that, but because these infections were hospitalizations were documented in every district or borough of the city, that means that by mid-February, there were infections in every borough of the city. Let me try the next slide. Now, I'm going to move from data on the counts of cases, which we all use to fit and project various models, to data from virologists. This is my interpretation of some data from virologists at MSHS, the Mount Sinai Health System. The question at hand here is, how could it be that cases were observed in every district of the city from the very beginning? Well, there are 2 alternative hypotheses. One is the hypothesis of multiple parallel importations. The virus did not appear originally in New York. People flew in from other countries and landed in New York and then propagated the virus. Is the wide dispersion of viruses or cases throughout the city from the beginning the result of multiple travelers arriving at basically the same time, but landing in disparate places? That's one hypothesis. The alternative hypothesis is that there was community transmission. That is, that one particular case seeded the entire epidemic, but there was rapid dispersion of that particular strain of virus throughout the city, what I would call a big bang. Well, it turns out of all of the samples analyzed by the Mount Sinai group, there was one clade, as it's called. I'll just point to that because the virologists use clade to refer to the genotype of the virus. It doesn't have any phenotypic significance. And that clade was the dominant clade that more than 2/3 of all the samples analyzed. And that clade, in their notation, A2A, came from basically from European countries, Spain, United Kingdom, France, Italy. And obviously the origin of those cases was not from France originally, but from East Asia. Among the 78 patients that they analyzed, their residencies, again, varied throughout the region. But among the 78, there were 17 cases in which the individuals had exactly the identical genetic signature. We've been talking a lot recently in the press about genetic variants. The variants are the result of mutations in the RNA or genetic code of the virus. And all of the pink bubbles represent a subset of those in the A2A clade that had a single base pair substitution in the open reading frame protein. This is not relevant, but for descriptive purposes, at position 1844, and the amino acid alanine was changed to valine. What this means for us is that all of these pink bubbles had the same exact tattoo, genetic signature. They were identical. And yet we can find them in Manhattan, Queens, Brooklyn, even Westchester, a county on the outskirts of New York, within days. The time axis is a bit different here because it wasn't until after approximately the 8th of March that the Centers of Disease and Control in the United States relaxed the criteria for testing individuals that allowed this kind of study to take place. So these data support the conclusion that although there were multiple importations from various sources in parallel, the dominant phenomenon was community transmission. That is, the propagation of the same strains of virus throughout the city with great rapidity. And the question is, how could that possibly have occurred? Okay. Let me move on. And now, let's see, okay. I am moving to the west coast of the United States for approximately 60 seconds. Not so much as to confuse people as to show a counter example. These are a series of maps of the propagation of coronavirus in Los Angeles County, where I am right now. I'm actually on Los Angeles, and so if I were to put my arrow, I'm approximately here. I'm on the edge of the initial focus of infection. And here, the West Coast is a bit delayed. So this is on March 16th. And here, without going into great detail, you can see the initial focus of infection. These are in relatively affluent areas. For instance, Beverly Crest, I think this one is here, where the median house price these days, well, before the epidemic was probably about $2 million. Here you can see 1 week later, radial spread around the initial focus. There are a few other dots here of other relatively affluent areas, but over time, the dominant phenomenon is radial spread from basically one small community to another. And then eventually the thing just, by the end of April, it's almost everywhere. What I'm saying is that the New York City case is unusual. The typical case, as reflected by Los Angeles, is there may have been multiple introductions, but one introduction became dominant and, in fact, propagated radially throughout the region. And in fact, although it would be a different talk, a spatial version of the SEER model, in fact, fits the data shown here. And that spatial version, in fact, shows that the transmission coefficients from one adjacent area to another are significant, especially during this initial take-up of the epidemic. From such a SEER model, we get an initial basic reproductive number in Los Angeles of about 2.7. I'll keep that in mind as I go forward. Okay. Here are now, we're going to combine some data on incidence of cases with data on the use of the New York subway system. The New York subway system is absolutely massive on a North American scale. The subway system in New York has an order of magnitude more rides per day, per week, or per year than the second largest subway system in the United States, which is in Washington, DC. The peach-colored dots represent the number of daily confirmed cases. So this is just raw incidence data. You might say right away, we have to fit it to a model. We'll do that soon. It's on a logarithmic scale for the main reason is that we can see here that there is a phase of exponential growth. Before that, there are problems with the data because the Centers for Disease Control, as I've said, have tended to we're restricting the criteria to people who came back from Wuhan, et cetera. So it's hard to know what's going on here. The sky blue bars are the volume of entries into the subway system. An entry does not count as an exit. So these are just one-way entries into the system. Here, in the final week of February, you can see just reading over here that there are about 6 million entries per day into the system. Now, there's some issues of timing here, although the basic message is, at least in the crudest sense of correlation, as the number of subway rides went down, the curve of the epidemic flattened off. What were the measures taken by public authorities during this time? Well, actually, nothing was done formally until both the mayor and the governor made announcements shutting down places of congregation, basically on March the 15th, and I'm drawing an artificial vertical line here, to go into effect March 16th. Yet we can see that even before the decree of the mayor of the city of New York, subway rides were already falling. And in fact, the velocity of the epidemic was already going down by the time the mayor made his announcement. Were this a study of what decisions were made at the public policy level, we would be inquiring further exactly what was happening here. But I think the message is that voluntary measures were being taken to reduce the use of the subway even before public authorities initiated measures to reduce social mobility. The mayor and no public official ever outlawed rides on the subway. They may have outlawed certain or stopped the use of certain sites where people congregated, and that may have had a secondary effect on travel. But the key point is, excuse me, these things occur before public authorities took any action. You can see here that as the epidemic appears, at least in the city as a whole, to become endemic at this point, with a reproductive number that looks like it's probably wavering around 1 around here, you can see that the volume of use in the subway is now 10% of what it was before the epidemic started. Now, the problem here is, as opposed to Los Angeles, which had data on each isolated community from the very beginning, the New York City database does not have that level of fine detail. Instead, the data for the very earliest phase of the epidemic are broken down only by district. And here we can see 2 districts, Queens and Manhattan. There's some noise here in the data because of restrictions on testing, but for both Queens and Manhattan, the line fits a doubling time of literally 1.1 days. And this is just by a least squares fit, combining the 2 data, which if we assume basically 1 over gamma equal to 5.5 days, then we end up with a basic reproductive number of 3.5. 3.5 is substantially greater than the estimates for communities like Los Angeles, which were close to 2.7. They're also greater than for estimates from Italy in the literature, but in fact, they're very close to the estimate for Wuhan, which also has a massive subway system. But we can see here that after about March 15th, the 2 districts diverge. And while actually for Manhattan, the darker dots, there may actually be some now diminution in incidence. In Queens, although the curve is flattened out, it's still going up a bit. And so let me stop and just talk about models. Models to describe the initial propagation of the virus may be very different from subsequent models that talk about the settling in or the continued epidemics in specific localities. And although I'm so used to fitting things to SEER compartmental models myself, the question here is whether or not this represents propagation along the edges of a network. And then finally, when we get to some local nodes in a network, then there is local propagation. Let me show you a map. This map is the earliest map that the city of New York has produced, where now the level of aggregation is by postal code, something that we had from Los Angeles from the beginning. And here, just to orient you, this is the borough of Manhattan. Here is the borough of Brooklyn. Here is Queens. There's the Bronx, and that's Staten Island. And there is a hotspot that has developed in Queens, whereas in the borough of Manhattan, there's nothing there. And this is basically, and this particular area here, which is the Elmhurst area of Queens, this area has such a high incidence. You're talking about an incidence here after just a couple of weeks of more than 100 per 10,000. That is already cumulatively, just relying on observed cases, we already have 1% of the population with confirmed cases. Here's just for, to follow up, here's what happens just even a week later. These are now the number of cases in different districts or different postal zones throughout the city, even 1 week later. And we begin to see a lot of spread throughout. But here I want to focus on this initial hotspot because it reflects the action that occurred in March. And I want to talk about the public transportation system, not only as the vehicle for the initial widespread community spread or propagation of the virus, but also I want to test the hypothesis that delays in emptying out the subway system attenuated the decline of the virus and led to the development of hotspots throughout the city. This is just my superimposing the lines of the subway on top of the initial graph. So I'll back up just for a minute. Here was the initial graph of the hotspot in Queens that I want to focus on for a few minutes. Here are the lines, the multiple lines of the subways that run throughout the city. This graph does not talk about the buses that extended from the city. To give you an idea, here's one line that starts in Manhattan. It's so much action in Manhattan, we can't disentangle it. It runs through here, it comes around here, and then it ends up at a stop on Jamaica 179th Street. There actually is a bus that runs from here all the way up to here. Okay, let me focus though on this subway line. I hope you can see it. It's all yellow lines here. This is the Flushing number 7 local, which goes back here and actually extends into Manhattan. Let me show you the next slide. Here is a blow up. Again, I have the hotspot of cases, and here I have changed the color scheme so that those subway stations which are located within the hotspot are yellow. Those in the remainder of Queens are pink, and the stations in Manhattan, including 5th Avenue, Grand Central Station, 42nd Street, are all in sky blue. Now, I want to look at the volume of subway use in these 3 different categories of stations. The yellow were the stations directly within the hotspot. The blue are the stations in Manhattan, and the pink are the other remaining stations within the borough of Queens. And there's a clear gradient here. Manhattan, the subway use literally emptied out, whereas in the stations where the hotspot developed, there is, although a decrease in subway use, a decrease by a significant amount, the fact is there's still some persistence in subway use. And a point at least suggesting for this hotspot that the decrease in subway use, although obvious, the fact that it was attenuated contributed to the development of infection in that particular area. Okay, well, that's fine, that's nice, but am I going to do this on a grand scale for the entire city? The answer is, well, we don't really have the data that on infection rates that early. And we have so many subway stations, how do we do this? And here's where I want to make the transition to mobility data. Here again is the same hotspot with the code numbers. The code numbers represent the postal zones. They're outlined in black. And then embedded within this as a finer gradation in blue, these are the census block groups, which are the subdivisions used by the US Census to carry out the census, but are also the tiles used by a source of mobility data called SafeGraph, which is widely used by investigators in the United States now. So although Olga talked about Facebook data where the tiles it sounded to me like they were basically squares on the chessboard, 400 by 400 meters, here the tiles are irregularly shaped, basically defined by streets and other administrative boundaries. However, it turns out that for the most part, although the postal codes are not totally congruent with the individual census block groups, the mapping isn't too bad. So if I could get data on social mobility in every census block group, I might then be able to map that into movements not between each blue irregular rectangle, but between each postal zone. So, okay, that's good. But the next problem is the data are movements of people. They are basically following smartphone devices. The devices send pings, which are collected. The person gives permission to follow them, to track them. But what is published basically are movements from one place to another, and necessarily either the origin or the destination has to be what is called the home of the device. That is the place, or basically blue rectangle, where the device spends the time overnight. There are no data on who took the subway, so I have a problem. I know what census block group the device came from, and where it went to, but I don't know whether they took the subway. However, I can identify the census block group of every subway station. And then I can test the hypothesis that a movement to the census block group in which the subway station was located is equivalent to taking a ride on the subway. And as it turns out, that is the case. There are two kinds of movements. Movements from people who are already within this small rectangle, or CBG. These are people who live there, and they may have gone to the subway, but they also went to the grocery store, or they went to have pizza. And their movements plotted here over time are basically just a stable line. However, the movements of any cell phone device that ended up in this specific census block group, whose geocode is here, track fairly well the actual number of subway rides which we can get from the Metropolitan Transportation Authority. Therefore, I have now a proxy for entry into the subway. Here, in fact, now what I've done is I've again zeroed in on the hotspot. I've marked only the stations of the subway that are in Queens. Manhattan has been erased from this map. Here are two particular stations which are in the commercial center of the borough of Queens. Here are the stations within the hotspot. And here are the origin, the census block groups whose origin went not only to one of these stations locally, but also to the commercial center of Queens. That is, the shaded regions, which are dark blue here, represent those regions which, in the greatest proportion, ended up making movements to the yellow dots and to these two pink dots. And we can see that, in fact, residents of the region that is the most, the hottest spot or the highest cumulative incidence of coronavirus infection, in fact, they took the subway and they went down to work over here, where the last sentence is obviously my inference as to what the data mean. All right, that is solely for one hotspot with a tremendous focus solely on a particular region. Can we generalize this? What I've done now is done the same exercise on a larger scale. For each and every postal code, I can find how many people who had made movements which originated in that code and ended up on a subway. And then I can compare that to the subsequent incidence of coronavirus. So on the horizontal axis here are the number of visits to the subway station census blocks groups in the middle of March, scaled as a percentage of the baseline. So a lot of them here, if I project downward to the horizontal axis, they're at about, by mid-March, they're at about 60% of their basic volume. Although down here, some of them by mid-March are already down to 25%. Here's an example. This is from Manhattan. That's the postal code for Manhattan. Some of them up in Queens here that start with 113 are up here. Here's one from Brooklyn. Here's another one from Brooklyn. On the vertical axis is the incidence of new infections 2 weeks later. And here in a simple ordinary least squares basic fit of the data, there is a significant relationship between the volume of subway use, as basically proxied by mobility data, and the subsequent rise or incidence of coronavirus infections. Here is some examples from 3, or actually for 4 of the postal codes where I don't have any data on incidence here, but you can see here's how I made the calculation. Basically, we start here where everybody is at 100%, that is every postal code is. At this cut here, I take mid-March, and that's how I differentiate the data. If I changed it from mid-March to some other date, the 15th or the 17th, it wouldn't make any difference. All right, well, that's a univariate. This curve is basically a univariate curve. And although there's a nice fit, there are some outliers here. And the question is, why are they outliers and what's going on? Well, borrowing from results in the study of Los Angeles, I found that the second most important predictor of coronavirus incidence had to do with population density, and in particular, the density of households that had multiple generations. So it's not merely the number of people from in each household, but it actually is whether or not the household has many people who are, some of whom are adults, let's say from 18 to 34, and then there's another generation which is older. And here is basically the map of the prevalence of these at-risk multi-generational households. And actually superimposed on this map is the graph, both of the postal zones and of the detailed census block groups. These data come from the US Census, but now what I can do is I can run a multivariate regression model in which I will, for each and every one of the postal zones, I can use both the degree of subway use and the prevalence of these multi-generational houses in order to predict subsequent coronavirus incidents 2 weeks later. The parameters here are not the parameters of an SIR model exactly. What they are is these are just the coefficients of a multivariate model in which both the dependent and the independent variables are logarithms. And beta 1 represents subway use. Beta 2 represents the prevalence of multi-generational households. This is basically my last slide, but there's something else on this slide. In addition to running just an ordinary least squares model, I ran models with spatial weights. That is, where adjoining postal zones were allowed to have influence on the coronavirus incidence of their neighbors. And in this case, I used a canned pre-written program in Stata that basically just said, if your postal zone is anywhere near you, north, south, or east, or west, it's hypothesized to have influence. And it turned out that those models, you don't see any bold-faced coefficients here for these other, other parameters. None of those models worked. Consistently, subway use and density of multi-generational households were the predictors of coronavirus incidents 2 weeks later, but adjoining postal zones had no effect. This seems to contradict what you would expect. After all, if I get on the subway at one stop and I stay on a crowded subway car, won't I infect somebody who gets on at another subway stop 2 or 3 stops later when I'm no longer in the hot zone? And the answer is we would expect that kind of propagation. The difficulty with this version of the model I've used is that this model takes into account adjacency or proximity in geographic space. I need to write a model in which we talk about proximity in transportation space. That is, I need to go all the way back here and I need to say a particular zone, postal zone, is proximate to another zone if they are joined by a subway line. That leads me to begin, and I will conclude here, or resume with the idea, perhaps we need to think about different models. We have a big bang that occurred very early in the epidemic in New York, in which the virus was propagated throughout the city by community transmission, apparently by one clade of virus. And to me, the best candidate to do that is the public transportation system. Then after the virus is propagated in particular areas, then it begins to settle down in ways that at least partly are compatible with a compartmental model. But to me, I'm now thinking that the right way to think about this would be a hybrid of both network models and compartmental models, rather than simply trying to fit these very unusual data, well, not very, well, yeah, very singular data in a pure SIR framework. Okay.
Right, thank you, Jeffrey, for a very nice talk. Of course, if you have questions, just raise the hand. There is a button below, and I will allow you to talk. So in the meantime, I'm quite curious to know why did you want to study a subway in the first place? Is there any reason? Or?
It was by basically looking at this, when I saw this picture.
Oh, so it's based on the data already.
This was the motivated empirical finding. I had started to look at New York City, and in particular, my first interest was, why did this curve bend down like this, and was it an artifact? And it turns out it may very well be that it substantially understates the number of coronavirus cases, but it's clear that the epidemic did flatten out rapidly from, in this case, a reproductive number of 3.5 within a short time to a reproductive number that we would guess here is close to 1. It's basically endemic. I just happened, I don't know, I think somebody was writing about the subway. Getting these data from the subway involved big data analysis. Calculating these volumes from the turnstiles was, it was not published in this way. It had to be reconstructed. But this basically was when I saw this, I said, something is happening here.
Right, I see. So it's a nice realization that, well, in a way, people are reacting before they don't wait for politicians to modify their behavior in a way.
I think there's a lot of evidence from economics that economists are thinking that what they would call coercive action by public authorities has an important component, but that voluntary action by individuals perceiving a risk is equally important in many cases.
All right. Thank you. I think Yvon has a question.
Yes, so thank you there for this very nice presentation of the evidence of the effect of the public transportation. Maybe I missed something, but do you have a matrix of departure destination with the R of where this passenger takes the public transportation in order to improve a little bit the understanding of the spreading of the illness through the epidemic, through the public transportation?
The answer, if I understand your question, is no. The New York City MTA collects data on entry into the system. Where that individual goes and what that individual's destination is, and where the individual exits the system are not recorded.
Okay.
I can think of many subways I've taken all over the place in which it is. I can even remember buying a token in Santiago, Chile, where in fact you had to specify where you were getting on and where you were getting off. And at least in principle, the transportation system there would keep track of origin and destination. Yeah. But in New York City, you can get entries and exits, and that's it.
Okay. Okay, this would be helpful. I think in London, it's possible also to have this. And maybe it might be interesting to get the information from London subway, because I think there is the beginning and the end of the destination.
Thank you. Thank you. Olga, you have a question?
Yes, thanks, Jeffrey. In fact, I was wondering, because in New York, you had a lockdown in March, right?
Yes, the lockdown, though, occurred, and I think I'll refer to this slide here.
So how can we disentangle the effect of the lockdown with the effect of taking the subway? Isn't this, shouldn't we rather understand this plateau related to the lockdown rather than directly on the subway? Because just to give a bit more of a context, with our Facebook data, we see we also had a lockdown, and we also record a dramatic drop in the movement between French regions and within a certain region like Paris. So we have a similar, we could similarly have the same plot, but instead of with the subway, just with movement of people. And I was wondering how can we disentangle both of them?
One could always argue, I think, because we have observational data, that the movements in public transportation are no more than a proxy for overall degree of social mobility. The best I can argue here is, first of all, when it comes to the mechanism of spread of the virus throughout the city, this was such a unique event that we need to think of what could have possibly been the vehicle for spreading the virus so widely. And that has less to do with the lockdown than this big bang phase initially. You could argue, this part of my response does not respond to your question. It really says there's another phenomenon, this phenomenon that needs to be explained. People have looked for super spreader events in New York, and the only one that I know of is basically an outbreak among the workers in the subway, which occurred basically at this time. The second source of evidence, and I'll go here, is that if we focus on a particular hotspot and we divide the subway stations into those stations within the hotspot, its periphery, and then far away, we seem to support the hypothesis that the attenuation of the decline in the use of the subway is correlated with a higher incidence of the disease. The last thing I can say is that aside from the fact that there is a correlation across regional areas between the volume of subway use in mid-March and subsequent incidence of coronavirus 2 weeks later, that in a multivariate model, and this is the last slide basically, where I consider to be the most important factor to be the presence of basically high density multi-generational housing, my variable for subway use is still more important than the others.
Okay, so in fact, this is the only source of movement that you had, in fact. Should I understand that, in fact, you didn't have other data to describe movements, and this was the best available for New York in your case, or
that I know of? Yes, that's
yes.
right.
Okay. Yes. No. Okay. I think I see. Yes. I understand. Thanks.
The particular hypothesis that the public transportation system was important in propagating the virus and in its persistence is not novel on my part. I've actually found 5 papers that already talk about this. 3 of the papers are in Wuhan, where there is an extensive subway system. And there are 2 other papers that have already been published. They're not even preprints anymore, that talk about this correlation. So, but those papers do not use mobility data, nor do they use data on analysis of genetic analysis of samples to look at the genetics of the virus. And so the contribution here really isn't to propose a hypothesis that hasn't been studied and tested before, but basically to talk about what I would consider basically the new form of epidemiology we're doing, where we're using diverse sources of evidence in order to inform our models. One other paper did use mobility data and basically found the same thing. Those regions in which individuals had the highest mobility from their origin for regions which had basically the highest incidence of coronavirus.
Okay, thanks.
Okay, so now we have a question from Jacques de Mongeau. Jacques, you can talk. Oh, can you talk?
No, I have not updated my micro.
Yeah.
And have you some evidence of percolation effects favored by the mobility? Local percolation, that is, you are reaching a certain threshold and suddenly the incidence is increasing, and have you remarked some percolation phenomena?
I'm not sure I understand your question. You're saying the incidence is increasing?
Yes, the percolation is due to the fact that during a certain time, for example, you have a stationary behavior of the disease, of the epidemic. And suddenly passing a certain threshold, in general, you are ignoring the value of this threshold. You have an increasing, very rapid increasing of the incidence of the disease that could be favored by this mobility due to metro or other way to pass from a side to another side, etc. You know this phenomenon of percolation in physics?
I think I understand you now. Let me go to this picture. So here we have rapid dispersion.
Yes.
And here we have what I'll call, borrowing from you, percolation.
Yes, probably.
And the question that I have not written one equation. I mean, the closest I've come to mathematical notation is to put a subscript here. Okay. But something tells me that this is a network model.
Yes.
This is not a compartmental model, although I could probably say every network model is a compartmental model. But I think this is a network model, and this is movement along the edges between nodes. And my hypothesis is the nodes are subway stations.
Okay, and you have probably reached this percolation threshold the 15th of March.
Something like that, that's right. Because here is the divergence between Manhattan, right? And it is arguable that in Manhattan, everybody has so much money and lives in such a high-end apartment building, and they have jobs where they can stay at home and go and work on Zoom. And
you are right.
Everybody has to get up and go to work and take the subway in order to deliver groceries or engage in housekeeping.
And do you know some network model you could use to represent this phenomena?
I have an image of a network model, but I have not formalized it.
Okay.
And part of my concern is that I would have expected that during this phase, I would see in a spatial model more effect of adjacent regions, which I did not see. And it is either because my metric for adjacency is wrong, or because there really isn't any spatial propagation. This is just percolation.
Okay. Thank you very much.
Can I ask a last question? Did you try to think about a model to describe the movement in the subway? Because it seems to me that you got the entrance in each subway, in each area, and so you could somehow have a sort of a model to describe the movement, some sort of starting from a given station or something like that, right? Did you think about that?
Yes, my difficulty is the limitations of the data. The raw data from the provider do tell us the origin and destination of every single movement. And all of the movements, basically, going back here, are from one small block on the grid to some other small block on the grid, right. Every one of them. But the data provided for public use to researchers is anonymized so that first, it's only aggregated. If you have small numbers, it won't show you that. And second of all all movements have to have either an origin or a destination, which is the device's home. So
yes, but with the origin only, you could, with the origin only already, with the input flux, if you want, you could describe, have some sort of model to say you are more likely to go around than very far away or something like that. You could have.
Yes, one investigator has tried basically to say, if you look at the regions that were more extensive here, and you look at movements from each one of these block groups, where we're talking about movements where the block group is the origin of the movement, which block groups have the most mobility? And again, that shows more mobility means more infection. But the problem is, if I have some data that people went from here to here, and I also have data that people went from here to there, I do not know whether or not the two sets are disjoint or whether those data represent movements from here to here and then to here.
Right.
I don't know that. The raw data show us that, but not the data publicly available.
All right. All right. Okay, that's what it is. Okay, thank you. Thank you.
Okay, so maybe if there's no more questions, it's time to close the seminar. Thank you, Jeffrey, again for participating in the seminar and for a very interesting talk. Thanks both the speaker, actually, Olga also, and also thank the participants for joining in. And I guess we'll see each other in about 2 weeks for next session. All right.
Before leaving, I just want to mention that Quentin will give a talk.
That's right. I will give a talk next time.
Please, and another young guy from Louisiana will give a talk. And so we will have two very young and active guys within 2 weeks.
Okay. Well, thanks everyone, and bye-bye.
Bye-bye.
All right.